All right.
Can you repeat that one more time? So you're saying under what is the condition under which we can get in the limit?
Right. So the condition we can exchange the limit and the derivative is that as t goes to infinity, the distance between two solutions with infinitesimally different parameters is not going to increase over time. The distance between them stays bounded. If that is the case, then you can exchange the derivative and the limit. That's usually not the case, right? So when you have slightly different parameters, the difference between the two solutions just grows exponentially, right? So when this is just superimposing the same thing, right? This is without shadowing, this is with shadowing. One has become wild, the other stick to each other. All right. Okay, so with the shadowing technique, this is the first adjoint we are able to compute out of a chaotic flow field. I mean, the first non-blowing up adjoint we are able to compute. So this is to have the first case, we did something really crude. So this is a solution of the Euler equation, not even the Navier-Stokes, over an airfoil with 90 degrees angle of attack. So it's completely just a flat plate. And basically, we are looking at the derivative of the drag with respect to everything you can perturb. And basically, we get a non-divergent flow field, and we get pretty good sensitivities. Again, one question we always have is what to compare with, because without the shadowing method, there is no other good ways of getting a sensitivity. The best way we figured out so far is doing linear regression, because we can compute a bunch of Mach numbers and get the objective function, in this case the drag, for these Mach numbers. But each one has an error bound, because you can only compute for so long, right? And you do a linear regression out of these error bounds. And you can argue linear regression may not be the right thing. You may want to do a quadratic regression, right? Because they are not expected to be linear and things like that. So actually, how to figure out what is the thing to compare is not an easy answer. But we figured out with 2,000 time steps, that's the long LSS, and short is 200 steps. With the long least square shadowing method, we get the right sensitivity. But the initial algorithm, which we did together with Nasa Langley, Boris Diskin, and Eric Nielsen, is very inefficient. So basically, just to find out the shadowing solutions, it took, of this very simple problem, it took 6 to 17 hours on 2,000 cores. So we successfully transformed a problem that can be solved on a single core to a supercomputing problem, which we hope we don't have to, right? So that motivated us to develop how can we do this more efficiently. Okay, and we also did this later on for a Navier-Stokes equation. So this is actually a proper Navier-Stokes solution, and we also have the adjoint working. So this is a chaotic adjoint of the time average, the lift, with respect to all the perturbations you can put to the flow field. It is one of the first non-divergent adjoints of a chaotic flow field.